Okay, so let's keep looking at this two-class case. Okay, so in the simplest case, for example, let's keep looking at you have two classes and you want to assign any input vector into one of the two categories. Okay, so this is going to be the input in this case is going to be two-dimensional. For example, let's assume that so let's turn this a little bit bigger. Oops. Okay, let's draw something here. Let's assume that X is in R2. Okay, so it's gonna be a plane, two-dimensional plane. So it's gonna be something like this. So turn it a little bit thinner so that I can draw better. X1 and X2, okay, two-dimensional. Okay, and basically we want to draw a single line in this case to divide the space into two parts. Let's just make an assumption that is going to be the simplest case. Okay, that something like this, maybe X2 equals to X1. Okay, and how do we rearrange this formula to make this look like this format? So basically, what we are going to do is that move it to one side. Okay, so X1 minus X2 equals to 0. Okay, that's going to be the formula. And how do we write this in the vector form? Is going to be 1 times X1 minus 1 times X2 equals to 0. So in the vector form is going to be like 1 minus 1. Oops. So in the vector form is going to be like 1 minus 1 times X1, X2. Okay, and we need an extra scalar here. Is going to be 0, equals to 0. So here it assigns to class C1 if Yx is equal to 0. Okay. So it's gonna be, let's see. In this case, this representation is gonna look like W is a two-dimensional vector, which is 1 minus 1, and X, okay, is basically composed of X1 and X2. So write it in a compact representation is going to be like Yx is equal to W transpose X plus 0, which is W0. Okay, so this thing is basically W0. So here, if it is greater than 0, which basically means that X1 minus X2 greater than 0, and it's going to be X2 smaller than X1. So it's going to be this part. So in this part, it's going to be assigned as class C1, and in other parts, this part, for example, is X2 greater than X1, which is assigned class C2. Okay. So W is called a weight vector, and W0 is the bias term. Okay, not to be confused with bias in the statistical science. The negative of the bias is sometimes called the threshold. An input vector x is assigned to class C1 if yx is greater than or equal to 0. To class C2 otherwise. The corresponding decision boundary is therefore defined by the relation, as we see here. Okay, in the scalar form, it's basically x1 minus x2 equals to 0. In the vector form, it's basically 1 minus 1, x1, x2 plus 0 equals to 0. Okay, so that's basically the decision boundary. It's defined by the relationship that this output yx is equal to 0. And you see this part is super important. It says that this decision boundary is a d minus 1 dimensional hyperplane. So for any d, it is the case. Let's take the 2-dimensional as an example here, right? So in this space, it's a 2-dimensional input space. Okay, so for any x, it has two components, x1 and x2. So it's a 2-dimensional space. Okay. But if we look at the decision boundary that separates this 2-dimensional space, it's actually just a straight line. Okay, a straight line is basically something 1-dimensional. So here, in our case, d equals to 2. So consider 2 points, any 2 points, both of which lie on the decision surface. So if we have a line, we have 2 points, xa, xb, okay? So both satisfy the condition that yxa equals to yxb equals to 0. Okay, so what do we have? Remember what is W here. So we are going to use this representation in the following derivation here. So we have something look like this. So if we write it out, W transpose XA equals to W transpose XB equals to 0. Okay, so in our case, W0 is 0. Okay, so YXA is basically W transpose times XA. Okay, YXB is basically W transpose times XB, and both equal to 0. So if we put both terms in one side, it's gonna look like W transpose XA minus XB equals to 0. Okay, which is the exact form that the author writes here. Hence, the vector W is orthogonal to every vector lying within the decision surface. Okay, what does it mean? So I think it has a visualization here, but let's look at our example here. So the vector W, if we write it out, remember it's 1 minus 1. So if we are going to represent it in this 2-dimensional space, what does it looks like? 1 minus 1, which is here, right? So if we draw an arrow, right, it's actually orthogonal to this decision boundary. So look at what the author said. Vector W is orthogonal to every vector lying within the decision surface. Basically, it's orthogonal to this decision surface. If we draw random 2 points and a connected line, basically this line, because it's again, it's a linear decision boundary, okay? So it overlaps with this decision surface. And this weight vector here is actually, this weight vector here is actually the one that is orthogonal to the decision boundary. Okay. So basically, W, because W is always orthogonal to the decision boundary or the decision surface. So it actually it actually decides the orientation of the decision surface. So whenever W changes to something else, okay, whenever W changes to something else, then the orientation of this decision surface is gonna change. What does it mean? So let's look at another example. So if we, for example, W is currently equal to 1, -1, and the decision boundary looks like this, right? If we change its orientation, W equals to, what should we do? 1, 1, okay? So it's gonna be x1 plus x2 equals to 0, which is 1, 1, x1, x2 plus 0 equals to 0. In this case, it's gonna be x2 equals to -1. So if we draw it here, x1, x2, and x2 equals to -x1, okay? So basically, if x1 equals to 1, x2 equals to -1. Okay, if x1 equals to 0, x2 equals to 0. So it's going to look like this. So W is actually something that decides the orientation of the decision surface here. This thing is very, very important. Okay. Similarly, if X is a point on the decision surface, so basically we have the entire equation being equal to the threshold, which is 0. Okay. So the normal distance from the origin to the decision surface is actually given by this. Okay. Normal distance from the origin to the decision surface is given by this formula. Let's derive it back, see if it actually makes sense. So if we multiply both sides by the absolute by W, okay, so we multiply by the norm of W, okay, so it's gonna be transpose X equals to W0, okay, those are vectors, so it's W transpose X plus W0 equals to 0, okay, so this is basically putting W0 into the other side and divide both part by the norm of weight vector. This is gone. Okay. Well, actually, it's not gone. Like actually, it's going to be a unit vector. Okay, its length doesn't matter, but its orientation matters. Okay, it's going to be a unit vector, points to the original direction of W. Okay, so here what it says is that we want to kind of eliminate the effect of its length, only focus on its orientation. Okay, so W trans X W minus W0 normalized by the norm of W. Okay, so basically this part is gonna be a unit vector with the direction of the weight vector. Okay, so as we can see that W0 controls the location of the decision surface. So if we change W0 up and change the W0, then this decision boundary is gonna move up and down, and that's basically the thing. And if we change the weight vector, then the orientation, the position won't change, but the orientation of the decision boundary is gonna change. Okay. So let's read through this paragraph. Furthermore, we note that the value of y-x gives a side measure of the perpendicular distance r of the point x from the decision surface. Okay. To see this, consider an arbitrary point x and let x be its orthogonal projection onto the decision surface. So for example, in this graph, I think it gives an example here. This is x, okay? This is x, and this right line here, this right line here, oops. This right line here is actually the decision boundary that the author provides. So we have x in a two-dimensional space, x1, x2, and we want x, okay, x orthogonal. I don't know how to call this notation, but let's just call it x orthogonal, okay? Be its orthogonal projection. So basically, it's going to be this point onto the decision surface. Okay. So let's look at this formula here. So what is R? Also say anything about R. Here's small r. So if we look at, I think we can look at it this way. So the weight vector W, okay, the weight vector, let's see, the weight vector W, okay, in the direction of it itself normalized by the norm of it, okay, so W is in this direction, okay, and a unit vector in the direction of self, basically orthogonal, as we talked about, is orthogonal to the decision surface, right? So the difference between these 2 points, x orthogonal and x, okay, as we mentioned, x orthogonal is the orthogonal projection of x on the decision surface. So the difference between the two is actually this part. Okay, that's the difference. And the direction of this part is actually the direction of W, because W is, as we discussed in the previous example, is actually the weight vector and is orthogonal to the decision surface. So that's going to be the direction that connects X orthogonal and X. Okay, and the rest left is basically some distance or the length between the two. Okay, and it uses the notation small r. Okay, so let's actually, I don't think it defines r anywhere before this formula, but let's look at it. Okay, so multiply both sides, but it doesn't matter, but you get the idea, right? The direction here actually matters. The difference between the 2 points is actually this line. Okay, this line is orthogonal to the decision surface, so it's going to be the direction of the weight vector plus multiplied by a by some length. Okay, by some scalar. Okay, so if you multiply both sides of this result by W transpose and adding W0 and making use of YX equals to W transpose X plus W0, okay? So what it looks like now. Let's do something following the instructions here, okay? So it's gonna be W transpose X equals to W transpose X orthogonal plus, okay, R, okay? Look at this. So it's gonna be R W transpose W divided by norm of W, okay? So it's gonna be, and also I think adding W0 here. So this part is gonna be YX, okay? And adding W0 here, okay? This whole thing is gonna be what, X orthogonal, okay? And you just, so W transpose times W is basically square of the norm, right? If it's, for example, L2 norm, okay? So it's gonna be R, okay, times multiplied by the norm of W, okay? So you connected the two, right? And by the way, this one, we notice that it lies on the decision boundary, so it equals to 0. So what we left is YX equals to RW L2 norm. So basically we are gonna have R equals to YX divided by L2 norm of W, which is exactly this part that the author pointed out. Okay. So yeah, basically now we derive what the length should be, okay, between x and x orthogonal. It's exactly yx divided by the norm of w. The norm of w could be simple L2 norm, okay? As with the linear regression models in chapter 3, it is sometimes convenient to use a more compact notation in which we introduce an additional dummy input value x0 equals to 1, and we define, basically we just increase the integrate everything into a kind of a three-dimensional vector. Okay, that's kind of a more compact representation. You can understand that way. So in this case, W is gonna be W0, W1, W2, and X is gonna be X0, X1, X2, but it's still two-dimensional because this one is a constant, right? It's not a variable. If it is variable, then it becomes a three-dimensional input, but this one is actually a constant. So it's still two-dimensional input, okay? And a two-dimensional input, and the decision boundary is still a one-dimensional thing. But it's just that for the convenience of writing out the equation, then we can integrate W0 into the larger vector W tilde here, okay? So in this case, the decision surfaces are d-dimensional hyperplanes passing through the origin of the d plus one-dimensional expanded input space. Well, you can understand it. It looks like three-dimensional, but it's not three-dimensional in a real sense because one of the dimension is actually fixed. It's a constant. It's not a variable. Okay. So now the authors in the next subsection tries to extend to the multi-classes case. So let's look at it. So consider the extension of the linear discriminants to k equals to a k bigger than two classes. Okay, now it's harder to do visualization, of course, right? We might be tempted to build a k-class discriminant by combining a number of two-class discriminant functions. Okay. However, this leads to some serious difficulties. So what it talks about is that if we have a few different decision boundaries, right? Then in theory we get kind of different areas, right? In this case, this one can be one category, okay? This one can be another category, and this part, oops, this color doesn't change. This part can be another category, okay? And oops, too close the color here. This one can be a third category, okay? And this thing can be the fourth category, okay? So basically, if you have two-class discriminant functions, then you may get a couple more categories or divided parts in the input space. However, the author mentioned that if you do this, this can lead to some serious difficulties. as we now show. Why is that? So consider the use of k-1 classifiers, each of which solves a two-class problem separating points in a particular class CK from points not in that class. So suppose we have C1, C2, and C3, okay? So one binary classifier can separate from C2 to C1 and C3. Another one could be separating from C1 to C2 and C3, right? This is known as actually the one versus the Rice classifier. The left-hand side example in figure 4.2 actually shows an example involve three classes where this approach leads to regions of input space that are ambiguously classified. Okay, so it's actually very similar to what I have drawn in the two-dimensional space. So if we look at this, right, let's think about this. So we have four different regions, right? We have four different regions. And one is separating, okay, this one, use some different, this one, okay? This one is separating from C1 and the rest of the categories, which is called not C1. Another one is separating from C2 to not C2, right? We may have a numerous number of different categories. We don't care. Now we take two categories as examples here, C1, C2, okay? So this part is C2. Let me try to draw it, okay? This much better. This part is going to be C2, okay? And this part, too similar, the color here, better color, this one. This part is going to be C1, okay? This part, it looks fine, right? Because it's not C1 and C2, maybe C3, C4, C5, whatever, we don't care. But the worst part is actually this green region, right? It's both C1 and C2. Now we are not choosing one from the list of categories, right? So this becomes ambiguous and causes conflict. So you see that the author mentions that when there are three classes, this approach actually leads to regions of input space that are ambiguously classified. Okay, so this is, according to our previous definition, this is both C1 and C2, which doesn't really make sense. So we can't simply just combine a number of different binary classifiers. An alternative is to introduce K multiplied by K-1 divided by two binary discriminant functions, one for every possible pairs of classes. Okay, this is known as a one versus one classifier. What does it mean? Suppose we have, let's see, we have three categories again, C1, C2, and C3. One classifier is maybe responsible for dividing between C1 and C2. Another one may be responsible for dividing between C2 and C3, right? It only cares the two classes, the two categories it tries to classify. It doesn't care the rest. And this is called one versus one classifier. each point is then classified according to a majority vote amongst the discriminant functions. However, this too runs into the problem of ambiguous regions as illustrated on the right-hand side. What does it mean? So we have this line, we have this line dividing between C1 and C3, okay? And we have this line dividing between C1 and C2. And further, we have the third line dividing between C2 and C3. Okay, the rest of the regions look good, right? But the center part of it, okay, according to this decision boundary, it should be C3. According to this decision boundary, it should be C1. Okay, according to this decision boundary, it should be C2. Right? Again, it's ambiguous. Okay, we can avoid these difficulties by considering a single K-class discriminant comprising K linear functions of the form, something like this. Okay, and then assigning a point X to class K, okay, to class CK if YK is greater than YJ for the rest of the categories, which is not true to itself, which is not itself. Okay. The decision boundary between class CK and class CJ is therefore, so if we want to kind of just focus on two categories, then it's basically a race condition between the two output from the two categories accordingly. We don't care the rest, right? We just care which value is higher. Is YK. If YK is higher, then it get the qualification to be compared with other categories. If YJ is higher, then it got the certification or the qualification to be compared with the other categories. Okay, and hence corresponds to a D-1 dimensional hyperplane defined by this thing. Okay, so basically we're moving Yj to left-hand side and set it equal to 0. This has the same form as the decision boundary for the two-class case as discussed in section 4.1.1. So analogous geometrical properties apply. If we just focus on two classes, the rest don't really matter, and it's kind of a Banner classifier again. The decision regions of such a discriminant are always singly connected and convex. To see this, consider 2 points, both of which lie inside decision region RK. Okay. As illustrated in 4.3, where is 4.3? It's actually here. Okay, so suppose that we got this a kind of comparison, the decision boundary formed by the highest value of the according category. Then suppose we have 3 regions accordingly corresponding to the decision boundary, and if we fall into this part is RK, and if we fall into this part is Ri, and if we fall into this part is Rj. Okay. Now we have the situation that if we have 2 points falling into the same decision region, which is XA and XB. Okay. The decision region of such a discriminant are always singly connected and convex. Okay, to see this, consider 2 points xa and xb, both of which lie inside decision region Rk. Any point lie on the line can be expressed as a form, right? So basically, it's kind of taking a weighted combination of xa and xb, right? So if you write it, for example, in the form that W1 equals to lambda, W2 equals to 1 minus lambda, we have actually W1 plus W2, or 1 to 2 Wi is equal to 1. Okay. So it's actually a weighted combination of Wa and Wb. And for any lambda that is greater than or equal to 0, less than or equal to 1, it must lie on the line that connected, straight line that connected the two. And you see that yeah, for the, so it's actually basically this form, okay? So remember that the output value for this winning class, let's call it winning class. The winning class is the category that gets the highest scores in terms of particular input. So XA obviously gets the highest output score on category K. So it's greater than the output of category J, right? Same case for XB. Okay. So it just tries to show, that it just tries to show that any point that fall onto on the straight line that connected XA and XB always fall into RK, okay? Because X, how to call it, X anchor, okay? X anchor here is actually a weighted combination of XA and XB, okay? So this thing is gonna greater than or equal to yi lambda yi xa, also greater than or equal to lambda y j xa. This thing here is greater than or equal to 1 minus lambda. This is something greater than 0, remember. So it's a positive coefficient. Yi xb also greater than or equal to 1 minus lambda yj sb. Okay. So this whole thing, yk x anchor is greater than or equal to yi lambda by yi xa plus 1 minus lambda yi xb, which is equal to y, let me see, yi x anchor. Same thing, it's greater than or equal to lambda beta lambda yj xa plus 1 minus lambda yj xb, which is greater than which is equal to yj x anchor. So for x anchor, yk still got the highest value. So yeah, basically that's the convexity, right? Note that for two classes, we can either employ the formalism discussed here based on two discriminant functions, y1x and y2x, or else use the simpler but equivalent formulation described based on a single discriminant function. We now explore three approaches to learning the parameters of linear discriminant functions based on these squares, Fisher's linear discriminant, and the perceptual algorithm. Okay. So least squares for classification. Let's look into this part. So in chapter 3, we considered models that were linear functions of the parameters. Okay. And we saw the minimization of sum of squares error function led to a simple closed form solution for the parameter values. For example, if you just think about linear regression, right? Basically, if you just minimize the sum of square error, okay, you can derive a closed form solution using normal equation, right? It is therefore tempting to see if we can apply the same formalism to classification problems. So consider a general classification problem with k classes with a 1 of k binary coding scheme for the target vector t. One justification for using least squares in such a context is that it approximates the conditional expectation of the target values given the input vector. Let's read this sentence again. So one justification for using least squares in such a context is that it approximates the conditional expectation of the target values given the input vector. Okay. What does it mean? Let's keep reading. For the binary coding scheme, this conditional expectation is given by the vector of posterior class probabilities. Okay. What does it mean? So we want something, perhaps if we have three categories, C1, C2, C3, we want a posterior possibility on the probability that this input class corresponds to each according category, 0.1, 0.2, and 0.7. The three sum to 1, right? Unfortunately, however, these probabilities are typically approximated rather poorly. Indeed, the approximations can have values outside the range due to the limited flexibility of a linear model, as we shall see shortly. So each class CK is described by its own linear model. Okay. This thing, where small k is inside the category from 1 to capital K. We can conveniently group these together using vector notation so that it can be written in a compact form, right? So what it means is that every category has its own corresponding output scalar. If we put them together into a vector, then basically yx is equal to y1x, y2x, y3x. Suppose it's a three class classification problem or three category, okay? And that basically corresponds to the according representation on the right-hand side, right? So W here, W2D is the matrix whose case column comprises the D plus one dimensional vector, okay? And X2D is basically dummy input value concatenated with the original input vector. So this representation was discussed in detail in the previous section. A new input X is then assigned to the class for which the output is the largest, okay? We now determine the parameter matrix by minimizing a sum of squares error function, okay? As we did for regression in chapter 3, right? If you're not familiar with linear regression, then basically you can go back and review that. That has kind of a closed form solution derived by normal equation. So consider a training data set xn, tn, where n is one data point from the training set, okay, the training data set, and define a matrix, a matrix T whose nth row is the vector T, subscript n, and superscript T, together with a matrix whose nth row is X2D and T. Some squares error function then can be written as this thing, right? So basically, this is the ground truth, and this thing is actually your prediction. And you're calculating the difference between your prediction and ground truth, and then take the square. And this is called sum of squares error function, right? And then at the very outside layer, outer layer, you take the trace, okay? So this coefficient 1/2, 0.5 is just for the convenience for you to write down the derivative. Okay. So setting the derivative with respect to W to 0, okay. Normally we just do this in order to calculate a optimum, minimum, right? And rearranging, we then obtain the solution for W in the form of this. This sounds like very familiar, right? Because it's just taking the derivative, setting the derivative to 0, right? And then derive the optimal solution for W, okay? So this thing is a pseudo inverse of the matrix X2D. Okay, we obtain the discriminant function in the form of this. Okay. No hard point at this up to now. So an interesting property of least square solutions with multiple target variables is that if every target vector in the remaining set satisfies some linear constraint, multiple target variables is that if every target vector in the training set satisfies some linear constraint, for some constants A and B, then the model prediction for any value of X will satisfy the same constraint. Okay. Thus, if we use a 1 of K coding scheme for K classes, then the predictions made by the model will have the property that the elements of Yx will sum to 1 for any value of X. And that's exactly something that we want, okay? We want actually probabilities, right? We want actually probability distribution, okay? However, this summation constraint alone is not sufficient to allow the model outputs to be interpreted as probabilities because they're not constrained to lie within the interval 0, 1. The least squares approach gave an exact closed form solution for the discriminant function parameters. However, even as discriminant function, where we use it to make decisions directly and dispense with any probabilistic interpretation, it suffers from some severe problems. We have already seen that least squares solutions like robustness to outliers, okay? And this applies equally to the classification application. So if we look at this, right, any kind of outlier will have a very large impact. We have a very, very large impact on the final derived solution. We already seen that least square solutions like robustness to outliers and thus applies equally to the classification application as illustrated in figure 4.4. Here we see that the additional data points in the right-hand figure produce a significant change in the location of the decision boundary. Okay. So if we look at this example here, right, it says that the left plot shows data from two classes, the right one, the blue one, right, denoted by red crosses and blue circles together with the decision boundary found by least squares here, okay, the magenta curve, and also by the logistic regression model, which is a green curve, okay. Logistic regression, which is something that we'll introduce, okay. The right-hand plot shows the corresponding results obtained when extra data points are added. So for example, if we have some outliers that are observed here, right, it has been added into this region, right? The right-hand plot shows the corresponding results obtained when extra data points are added at the bottom left. The diagram shows that least squares is highly sensitive to outliers unlike logistic regressions. So what is the magic behind logistic regression? We will see that, okay? Kind of tries to maximize the likelihood, okay? So you can see that the green curve, the green line here, okay, the green line here, which is actually the decision boundary given by the logistic regression model, is still kind of staying at a relatively stable position. But this magenta curve, magenta straight line, deviates a lot when there are outliers, which shouldn't be, right? Even though these points would be correctly classified by the original decision boundary left-hand figure. Okay. Next paragraph, continue talking about this. However, problems with least squares can be more severe than simply lack of robustness. Okay, let's look at 4.5, right? So example of a synthetic data set comprising of 3 classes. By the way, I really like the visualization in this book. It's kind of, gives perfect examples to some concepts. So definitely utilize them when you actually read through the book. Okay. When training data points denoted in red, green, and blue. So here you see 3 clusters of data points, red, green, and blue. Lines denote the decision boundaries and background colors denote the respective classes of the decision regions. Okay, on the left is the result of using least squares discriminant. Okay, we see that the region of input space assigned to the green class is too small, and the majority of the green points are misclassified. So you see here, this area of green data points and this area of green data points are both misclassified as blue ones and red ones accordingly. On the right-hand side is a result of using logistic regressions, showing, so basically you can see that it's very well classified, right? This part and this part, these two decision boundary, it almost perfectly separates the 3 classes. So let's continue reading. This shows a synthetic data set drawing from 3 classes in a 2-dimensional input space, having the property that linear decision boundaries can give excellent separation between the classes. Indeed, the technique of logistic regression described later in this chapter gives a satisfactory solution, okay, as seen in the right-hand plot. However, the least square solution gives poor results with only a small region input space assigned to the green class. The majority of the green points are just misclassified. The failure of least squares should not surprise us when we recall that it corresponds to maximum likelihood, okay, under the assumption of a Gaussian conditional distribution, whereas binary target vectors, okay, clearly have a distribution that is far from Gaussian, okay? By adopting more appropriate probabilistic models, we shall obtain classification techniques with much better properties than least squares. We shall obtain classification techniques with much better properties than least squares. Okay. For the moment, however, we continue to explore alternative non-probabilistic methods for setting the parameters in the linear classification models. So as we will see later on, that probabilistic measure is actually a wonderful way to do multi-class classification, okay? It's 9:34 p.m. in Toronto, so I'm gonna wrap it up here. So tomorrow I'm gonna continue the live stream, okay, and keep reading through the pattern recognition machine learning book with all of you. So thanks for listening, and see you soon.